Hello students, I hope you all are doing good. So our today's topic is alternating currents NCERT exercise. This is a disclaimer. So after this lecture you will be able to calculate RMS values and peak values in AC circuits and understand how current flows through basic circuit components, resistors, inductors and capacitors when connected to AC supply. Understand the reactance in AC circuits and its relationship with frequency and calculation of resonant frequency in AC circuit. So index, there are total 8 NCERT exercise questions in chapter alternating current. In this lecture, we are going to cover all of these questions 7.1 to 7.8. So let's start with first question. So a 100 ohm resistor is connected to a 220 volt 50 hertz AC supply. Okay, so this 220 volt, it is not mentioned whether it is peak value or RMS value. Okay, so if it is not mentioned in the question, it has to be taken RMS value. So it is connected to 220 volt RMS value of voltage, 50 hertz AC supply. So you have to calculate what is the RMS value of current. RMS value of voltage is given. RMS value of current you have to calculate in the circuit, and also what is net power consumed over a full cycle. Okay, so I will give you some time to think about it. So let's see the solution. So what is given in the question? First one is resistance of the resistor is given R equal to 100 ohm. Supply voltage V equal to, and it is not mentioned, then it has to be taken VRMS, which is equal to 220 volt. Frequency nu is given equal to 50 hertz. Okay, RMS value of current will be equal to IRMS equal to VRMS upon R. This is purely resistive circuit, only resistor is connected. So IRMS will be equal to VRMS upon R, NCERT equation 7.9. So IRMS will be equal to 220 upon 100. So IRMS is 2.2 ampere. Okay, now B part, what is the net power consumed over a full cycle? Hence RMS value of current is 2.20 ampere. So B part, net power consumed over a full cycle is given by the average power over a complete cycle. So from relation of average power for purely resistive circuit. So for pure resistive circuit, average power is given by VRMS, IRMS, cos phi. Okay, for purely resistive circuit, it is only VRMS, IRMS. Okay, cos phi is not necessary to write here. But we have written because we are doing exercise and we don't know which type of circuit is this. Then for resistive circuit, this phi will be equal to 0 because phase difference between current and voltage in the case of pure resistive circuit is 0. So cos phi will become 1, and eventually this equation will become P dash equal to average power is equal to VRMS IRMS according to NCERT equation 7.30a. So for purely resistive circuit, phi equal to 0 degree. So cos phi will be 0. So average power will be 220 into 2.2. So average power will be 484 watt. Okay. Hence average power consumed over one complete cycle is 484 watt. So average power is dissipated across resistor only. If there is another circuit, if there is a capacitive circuit, purely capacitive circuit or purely inductive circuit, then average power consumed over full cycle will be 0. So next exercise 7.2. Question A part is the peak voltage of AC supply is 300 volt. So peak voltage is given. You have to calculate the RMS voltage. Okay, we can calculate. We know the relation between RMS and peak value of voltage and current. Okay. Also B part, the RMS value of current in an AC circuit is 10 ampere. What is the peak current? So both the parts are identical. We know the relation between RMS and peak value. Okay, and if for any quantity RMS value is given, so peak value will be equal to root 2 into RMS value. So in A part, peak voltage is given, we have to calculate RMS value, and in B part, RMS value of current is given, we have to calculate peak current. So I will give you some time to solve it. So let's see the solution. So peak voltage of AC supply VM is given 300 volt. Now RMS voltage is given as Vrms equal to Vm upon root 2. This is the relation of between RMS value and peak value according to NCERT question 7.8. So RMS value will be equal to 300 upon root 2. So what is the value of root 2? 1.414 approximately. Okay. So Vrms will be equal to 212.1 volt. Okay. Similarly, so RMS value of voltage is 212.1 volt. Similarly, we will calculate the peak value of current. So RMS value of current IRMS is given equal to 10 ampere. Now peak current is given as, so peak current will be the relation between RMS and peak. So IRMS will be Im upon root 2, and Im will be equal to root 2 into IRMS according to NCERT equation 7.6. So IRMS is given 10 ampere. So peak value of current Im will be equal to root 2 into 10, which will be equal to 14.1 ampere. Okay. So peak value of current is 14.1 ampere. Now next exercise 7.3. A 44 millihenry inductor L is given. 44 millihenry inductor is connected to 220 volt 50 hertz AC supply. Determine the RMS value of current in the circuit. Okay, so this is a case of purely inductive circuit because no other component is present. So 44 millihenry inductor is connected to a AC source, and specifications of AC source are given. 220 volt is considered as RMS value because it is not mentioned that which value is this, peak value or RMS. So by default we have to take it as RMS value. So you have to determine the RMS value of current in the circuit. So I will give you some time to solve it. So what is given in the question? Inductance of inductor is given L equal to 44 millihenry, which is equal to 44 into 10 raised by minus 3 Henry. Supply voltage, which is VRMS value, equal to 220 volt. Frequency nu is given equal to 50 hertz. Angular frequency omega equal to 2 pi nu. And to calculate the RMS current, we need inductive reactance first. So to calculate IRMS will be equal to VRMS upon XL in the case of purely inductive circuit. Okay, so to calculate the IRMS, we have to calculate the XL first. So omega is 2 pi nu. So we will calculate the omega also. So inductive reactance is given by XL equal to omega L. Okay, so NCERT equation, according to NCERT equation 7.13, and omega is 2 pi nu, so XL will be equal to 2 pi nu L. So put the values of nu and L in the expression of inductive reactance. So XL will be equal to 2 pi into 50 into 44 into 10 raised by minus 3. Nu is 50, L is 44 into 10 raised by minus 3. So XL will be equal to 13.82 ohm. Okay, now we can calculate the IRMS current. So RMS value of current is given as IRMS equal to V upon XL. XL will be equal to XL, we have calculated 13.82 ohm. So put this value. So IRMS will be equal to 220 upon 13.82. So IRMS will be approximately equal to 15.92 ampere. Okay, so RMS value of current in the circuit is 15.92 ampere. Okay. So next exercise 7.4. A 60 microfarad capacitor is connected to a 110 volt 60 hertz AC supply. Determine the RMS value of the current in the circuit. Okay, so this is the case of purely capacitive circuit. Okay, in this, a capacitor of 60 microfarad capacitance, what is given? C is given. Okay, 110 volt connected to a 110 volt supply. 110 volt here is, it is not mentioned, so it is VRMS, RMS value of voltage, and 60 hertz is frequency of the AC circuit, nu. So you have to determine the RMS value of current. In previous question, what was given? Inductor. In this question, capacitor is given. Method is same. So I will give you some time to solve it. So let's see the solution. So what is given in the question? Capacitance of capacitor C is given 60 microfarad, and micro is 10 raised by minus 6. So 60 into 10 raised by minus 6 farad. Supply voltage is given as V, which is equal to VRMS value, and it is given as 110 volt. Okay, so in Indian households, 220 voltage of 220 volt, that potential difference or voltage is being used, means home appliances are operated on 220 volt. But in USA or maybe in other countries, in households, appliances are operated on 110 volt voltage. Okay, so supply voltage V equal to VRMS 110 volt. Frequency nu is equal to 60 hertz. angular frequency is omega is equal to 2 pi nu. And we know that to find the RMS value, we have to find the capacitive reactance first. That is Xc. Xc we know that 1 upon omega c. Omega is 2 pi nu. Okay, so Xc will be, so capacitive reactance is given by Xc equal to 1 by omega c according to NCERT equation 7.17. Okay, so this omega will be 2 pi nu. So Xc will be equal to 1 by 2 pi nu. Like this. So Xc will be equal to 1 upon 2 pi nu c. Now put the value of nu and c in the expression of Xc. So Xc will be 1 upon 2 into pi is 3.14, nu is 60 hertz, and c is given 16 times by minus 6 farad. Okay, so after calculating it, Xc will be equal to 1 upon 6.28 into 10, 360, 3600, 3600 into 10 by minus 6. Okay, so Xc will be equal to 1 upon 2.26 into 10 by minus 2 ohm. And finally, capacitive reactance and RMS value of current is given as IRMS equal to VRMS upon Xc according to NCERT equation 7.18. Okay, now put the value of Xc that you have calculated. So we have not calculated the Xc value completely because we are going to put it here and then completely solve it. Okay, so putting the value of Xc which we have calculated 1 upon, why we have kept this value of Xc without solving it completely, because Xc is in the denominator. So 1 by 2.26 into 10 to the minus 2, it will go in the numerator when we'll put this value in the final expression of IRMS. So Xc is 1 upon 2.26 into 10 to the minus 2 ohm. So put this value in the expression of IRMS, it will become VRMS is 110 volt and Xc 1 by Xc will be equal to 2 into 10 2 into 26 into 10 power 2.26 into 10 power minus 2. Okay, so IRMS will be equal to 2.49 ampere after solving it. Okay. Hence, the RMS value of current is 2.94 ampere. Got it? Now, next question in exercise 7.3 and 7.4. In 7.3, what we have discussed? A pure inductive circuit having inductor, okay, of inductance 44 millihenry. And in exercise 7.4, we have calculated the IRMS for purely capacitive circuit of capacitance 60 microfarad. Okay, so in exercise 7.3 and 7.4, what is the net power absorbed by each circuit over a complete cycle? So for inductive circuit and for capacitive circuit, what is the average power absorbed over a complete cycle? Explain your answer. Okay, in theory section, we have discussed that average power absorbed over a complete cycle in inductive or purely capacitive circuit is 0. But here we have to calculate it mathematically and explain our answer. So exercise 7.3, what was exercise 7.3? What was given in the exercise 7.3? A 44 millihenry inductor is connected to 220 volt 50 hertz AC supply. And in exercise 7.4, what was given? A 60 microfarad capacitor is connected to 110 volt 60 hertz AC supply. Okay. So I will give you some time to think about it. Let's see the solution. So net power consumed over a full cycle is given by average power over a complete cycle, which is P dash equal to Vrms Irms cos phi. Okay, so this is general expression for the average power. So we will see what is the power factor for purely inductive circuit, purely capacitive circuit, or purely resistive circuit according to the given in the question. Okay, now in the question, in one case there is purely inductive circuit, in second case there is purely capacitive circuit. So we'll modify this cos phi according to that. General expression is this for average power according to NCERT question 7.30a, where phi is the phase difference between voltage and current. In pure inductive and capacitive circuit, current and voltage are out of phase. Okay, so we have discussed that with the phase diagrams, we have discussed that phase relationship between current and voltage in the case of inductive and capacitive circuit. And in both these circuits, current and voltage are out of phase by pi by 2. Means in inductive circuit, voltage leads the current by pi by 2, and in capacitive circuit, current leads the voltage by pi by 2. So in both cases, phase difference between voltage and current is pi by 2, and cos pi by 2 is 0. Okay, in case of capacitive, current leads. Okay, so phi was pi by 2. In inductive circuit, current lags. So phi was minus pi by 2. Okay, but it doesn't matter that it is minus pi by 2 or pi by 2, because cos minus pi by 2 or cos pi by 2 both is equal to 0. Okay, so cos power factor for both capacitive and inductive circuit will be 0. That means average power consumed will be 0. Hence average power consumed over a complete cycle will be 0. That is the net power is 0. So next question. A charged 30 microfarad capacitor is connected to a 27 millihenry inductor. What is the angular frequency of free oscillations of the circuit? Okay, so there is a capacitor of 30 microfarad capacitance which is connected to, now what is this type of circuit? This is LC circuit. Only inductor and capacitor is connected, no resistor is there. So you have to calculate the angular frequency of free oscillations of the circuit. So you have to calculate the omega. Okay, so I will give you some time to think about it. So let's see the solution. So what is given in the question? Capacitance C is equal to 30 microfarad, which is equal to 30 into 10 to the minus 6 farad. Inductance L equal to 27 millihenry, which is equal to 27 into 10 to the minus 3 henry. Term angular frequency of free oscillation means frequency equivalent to resonance frequency. Okay, so you have to calculate the omega naught. Okay, free oscillations means resonance condition. So angular frequency of free oscillation means frequency equivalent to resonant frequency. That is, you have to calculate the omega naught, which is given by omega naught equal to 1 by root LC NCERT equation 7.28. So what is the condition for resonance? We have to remind it. So at resonance, Z is minimum because XL becomes equal to XC. And if Z is minimum, that means current is maximum in the circuit. Okay, and at this condition, inductive reactance is equal to capacitive reactance. That means XL equal to XC. Omega L equal to omega naught L equal to 1 by omega naught C. So after solving this or rearranging this equation, omega naught came out to be 1 upon root LC. Okay, so this is the expression for resonance frequency. Now put the values of L and C in this equation. So omega naught will be equal to 1 upon root 27 into 10 to the power minus 3 into 30 into 10 to the power minus 6. So omega naught will be equal to 27 into 3, 81. Okay, and 10 to the power minus 3 into 10 to the power minus 6 will be 10 to the power minus 9 into the 110, that is along with this 30. 30 you have to divide it 3 into 10. So that 10, it will make 10 to the power minus 8, and 27 into 3 will make 81. So root 81 is 9. Okay, so after solving this expression, omega naught will be equal to 1 by root 81 into 10 to the power minus 8. So omega naught will be 1 upon 9, and 10 to the power minus 8 root, taking root, it will become 10 to the power minus 4. So omega naught will be equal to 1.11 into 10 to the power 3 radian per second. So this is the angular frequency of free oscillation, means frequency of AC circuit equivalent to the resonance condition. So it will be equal to, so angular frequency of free oscillation of the circuit is 1.11 into 10 to the power 3 radian per second. Okay, so let's see the next question. A series LCR circuit with R equal to 20 ohm, L equal to 1.5 Henry, and C equal to 35 microfarad is connected to a variable frequency 200 volt AC supply. So what is meant by variable frequency 200 volt AC supply? So variable frequency means frequency is changing, frequency is not fixed. We, in previous question we have discussed, we have mentioned, there was mentioned in the question that 50 hertz, 60 hertz, that means fixed frequency AC circuit, but this is variable frequency AC circuit. Okay, and 200 volt AC supply means this is given RMS value of voltage, and all the three components, resistor, inductor and capacitor, are connected in the circuit. So resistor R is equal to 20 ohm, L is equal to 1.5 Henry, and C equal to 35 microfarad is given. When frequency of the supply equals the natural frequency of the circuit, what is the average power transferred? So what is this condition? When the frequency of the supply equals to the natural frequency of the circuit. So what is this condition? Resonance. When natural frequency matches the frequency of the supply. At this frequency, current in the circuit becomes maximum and impedance becomes minimum. So this is the condition of resonance. Then at resonance, what is the average power transfer to the circuit in one complete cycle? Okay, so you have to calculate this. So I will give you some time to think about it. So firstly, list all the things. So what we have to calculate? We have to calculate the impedance. Okay, then we have to calculate the IRMS. VRMS is given. Then we have to calculate the average power transferred. Okay, so what is given in the circuit? Resistance R equal to 20 ohm, inductance L equal to 1.5 Henry is given. Capacitance C is given equal to 35 microfarad, and which is equal to 35 into 10 to the power minus 6 farad. and applied AC voltage to LCR circuit V equal to, and it is not mentioned that it is peak or RMS, so by default it is RMS value, which is 200 volt. So at resonance, so I have mentioned what type of condition it is given, then when frequency of supply equals to natural frequency. They didn't mention directly that it is resonance, but they have twisted their words. Okay, so that is the condition of resonance. So at resonance, applied frequency is equal to the natural frequency of the given LCR circuit. So what is the impedance relation? So what is the expression for impedance in the circuit is given by the relation Z equal to root R square plus XC minus XL square, according to NCERT equation 7.26. At resonance, XL is equal to XC. Okay, we know that at resonance impedance becomes minimum. So how impedance can be minimum? When XC becomes XL equal to XL, means XC minus XL will become 0, due to which this Z will become minimum and it will become equal to R, resistance, and current in the circuit becomes maximum. So Z at resonance will be equal to R square plus 0 square, which is equal to R square only. So Z is equal to R, which is equal to 20 ohm. Got it? So impedance at resonance is calculated as equal to resistance, which is equal to 20 ohm. Now current in the circuit can be calculated as, so how do we calculate the current in the circuit? So IRMS will be equal to VRMS upon Z, and at resonance condition we can write R at the place of Z. So putting the value of Z, which we have calculated 20 ohm, and putting the value of VRMS, which is given in the question, which was equal to 200 volt. So IRMS will be equal to 200 upon 20. Okay, so RMS value of current in the circuit is given as 10 ampere. Okay, so average power in one cycle in series LCR circuit at resonance is given by. So now we have to calculate the average power in the LCR circuit in complete cycle. At what condition? At resonance. So average power expression is given by IRMS, VRMS, cos phi. Okay, at resonance, R becomes equal to, Z becomes equal to R. So cos phi is equal to, according to impedance diagram, cos phi is equal to R upon Z. If Z becomes equal to R at resonance, then cos phi will be equal to 1. That means average power will be equal to IRMS VRMS. Same expression we discussed in the purely resistive circuit. In purely resistive circuit, also average power dissipated is equal to the IRMS VRMS. Okay, so means at resonance, circuit will behave like purely resistive circuit, and average power will only be dissipated across the resistance in resonance or without resonance condition also. Okay. At resonance, phase difference phi is 0 between current and voltage. Okay, at resonance, current circuit start behaving like a purely resistive circuit. Okay, and in purely resistive circuit, we know that phi is 0. Phase difference between voltage and current in the case of purely resistive circuit is 0. That means cos phi will be equal to 1. Also, we can solve it by another method, that cos phi is equal to R by Z. Z is equal to R at resonance. That's why cos phi is R upon R, which is equal to 1. We can solve by this method also. Okay, and by this method also, that phi is 0 because current and voltage are in phase at resonance. That means cos 0 degree is 1. So average power will be equal to IRMS VRMS into 1. So it will be equal to IRMS VRMS. So average power IRMS is given. IRMS we have calculated, which was 10 ampere. VRMS was given in the question, 200 volt. So 200 into 10. So average power dissipated will be equal to 2000 watt, or we can write it as 2 kilowatt. 2 kilowatt. Okay, so hence the average power transferred to the circuit in one complete cycle is 2000 watt, and this power will be dissipated across resistance only. Okay, because average power dissipated across capacitor and inductor is 0. And reason we know, in case of capacitor, in positive, in one quarter cycle capacitor is being charged, due to which energy is stored. In one other quarter cycle capacitor is being discharged and the energy stored will be returned. In the case of inductor, when current increases, magnetic flux through the inductor will increase, due to which magnetic energy is stored. When current decreases, current magnetic flux through the inductor will decrease. Okay, so same amount of energy is returned as it stored, due to which average power or average energy across inductor or capacitor will be equal to 0, but it is dissipated across resistance only. Okay, and in at resonance we have calculated what is the average power transfer to the circuit in one complete cycle. It is given as 2000 watt. Okay, now next question. So figure is given, and question is figure 7.17 shows a series LCR circuit connected to a variable frequency 230 volt source. Okay, so variable frequency is there. Also in this question frequency is not constant. So variable frequency 230 volt source, and it is the value of VRMS. L is given 5 Henry. Capacitor is given, capacitance is given of capacitor which is 80 microfarad. Resistance is given equal to 40 ohm, and it is shown in the diagram. So it is a series LCR circuit connected to a AC source. Determine the source frequency which drives the current in resonance. So you have to calculate the source frequency at which condition? At resonance condition, due to which circuit came to resonance condition. Circuit will operate at resonance condition. So you have to calculate the source frequency for that. So what should be the source frequency? Source means through which we are taking current. Okay, so what should be the source frequency that circuit will be operated at resonance? B part, obtain the impedance of the circuit and the amplitude of the current at resonant frequency. So at resonance frequency omega naught, which is equal to 1 upon root LC. So you have to calculate or obtain the impedance of the circuit at resonance, which we know what is the impedance at resonance, becomes equal to resistance of resistor connected in the series with capacitor and inductor. Okay, and amplitude of current you have to calculate, means Im. C part, determine the RMS potential drop across the three elements of the circuit. So across all the components, resistance, capacitor and inductor, you have to calculate the RMS potential drop, VRMS, across all the components. Show that the potential drop across the LC combination is 0 at resonant frequency. So combined, or we can say effective potential drop across both LC combination, L and C, not resistor, only LC. Across LC the potential drop will be 0 at resonant frequency. Okay, only potential drop exists at across resistor in the case of resonance. Okay, so you have to determine it or you have to prove it. So I will give you some time to think about it. So let's see the solution. So what is given in the question? Inductance of the inductor L equal to 5 Henry is given. Capacitance of capacitor C equal to 18 microfarad, 80 microfarad, which is equal to 18 to 10 to the power minus 6 farad. Resistance of the resistor R equal to 40 ohm is given. And source voltage VRMS equal to 230 volt is given. So A part. So you have to calculate the source frequency which drives the circuit in resonance. So resonance angular frequency is given as omega naught equal to 1 by root LC. Okay, this is the expression for resonance angular frequency. And this expression is in accordance with NCERT equation 7.28. So we will calculate omega naught first, then we will calculate the nu naught. You have to calculate the frequency only, source frequency, not source angular frequency. So firstly we will calculate the source angular frequency omega naught, then we will calculate the nu naught. Okay, so after substituting all the values, you will get omega naught will be equal to 1 upon root 5 into 80 into 10 to the power minus 6. Okay, so omega naught will be equal to 1 upon root 400 into 10 to the power minus 6, and root 400 is 20, and 10 to the power minus 6 root will be equal to 10 to the power minus 3. So omega naught will be equal to 10 to the power 3 upon 20. Okay, in denominator it is 10 to the power minus 3. In numerator it will, when it will go to numerator, it will become 10 to the power 3. So omega naught will be equal to 1000 upon 20. It will become equal to 50 radian per second. Now we will calculate nu naught. So hence the circuit will come in resonance for a source frequency of 50 radian per second. Okay. B part. Impedance of the circuit is given by the relation Z equal to root R square plus XL minus XC square. So we have to calculate the impedance and amplitude of the current at resonant frequency. Okay, at omega naught we have to calculate the Im and Z. So Z is equal to root R square plus XL minus XC. So to calculate the Z impedance of the circuit, we have to calculate the XL and XC first. So this formula is in accordance with NCERT equation 7.26. So at resonance, XL is equal to XC. So it is resonance condition, so you don't have to calculate XL and XC. Okay, if it is not resonance condition, you have to calculate XL and XC, but it is resonance condition, so they will get cancelled out. Difference of both XL and XC will be equal to 0, so we don't have to calculate it. So at resonant, XL equal to XC and R is equal to 40 ohm given in the question. So Z will be equal to root R square plus 0 square. So Z will become equal to R, which is equal to 40 ohm. So at resonant, impedance of the circuit will be equal to resistance of the resistor connected in series with capacitor and inductor. So at resonance, impedance Z of the circuit is 40 ohm. Okay, now we have calculate the amplitude of current. So amplitude of current at resonant frequency is given as Im equal to Vm upon Z. So this is NCERT equation 7.25b. So we can write it as IRMS equal to VRMS upon Z, and we can also write it in the terms of peak value, which is Im equal to Vm upon Z. So peak value of voltage is not given in the question. VRMS is given. So we'll find peak value of voltage from RMS. So Vm will be equal to root 2 VRMS. This is the expression between peak value and RMS value according to NCERT equation 7.8. So put the value of Vm in the expression of Im equal to root 2 VRMS upon Z. Now VRMS is given 230 volt. Also Z is given. What is Z? Equal to R at resonance, which is equal to 40 ohm. Now putting the values of VRMS and Z, we will get Im equal to root 2 VRMS upon Z equal to root 2 into VRMS, it's 230 upon Z is 40 ohm. Okay, now Im will be equal to, after solving it, 8.13 ampere. Got it? So we have calculated the amplitude of the current in this B part. Hence resonance of amplitude of current is 88.13 ampere. Now C part. We have to calculate the potential drops across the three elements of the circuit, and you have to prove that potential drop across LC combination is 0 at resonant frequency. Only potential drop across resistor will appear at resonance. So RMS potential drop across inductor at resonant frequency can be given as VL RMS. So potential drop across the inductor will be equal to VL RMS, which is equal to IRMS XL, which is equal to IRMS, what is XL? Omega naught L. So omega naught is at resonant frequency. So at resonant frequency, RMS value of potential drop across the inductor is given as IRMS omega naught L. Okay, now IM is, we have calculated 8.13. So IRMS current can be given as, peak value of current we have calculated at resonance frequency. So IRMS will be equal to IM upon root 2, which is equal to 8.13 upon root 2 ampere. Okay, so no need to solve it further. We will solve it in the final expression when we are going to calculate this VL. Okay, so kept it as it is, 8.13 upon root 2 ampere. Now we have to calculate the VL RMS. So putting the value of IRMS and omega naught in the VL RMS equal to IRMS omega naught L. Okay, L we are given in the question, L equal to 5 Henry. So VL RMS will be equal to IRMS, which was equal to 8.13 upon root 2. We have calculated in the previous slide, into 50, which is resonant frequency, and multiplied by 5, which is given value of inductance, L equal to 5 Henry. So after solving it, VL RMS value across, RMS value of voltage across the inductor is equal to 1437.5 volt. Okay, hence RMS potential drop across the inductor at resonating frequency omega naught will be 1437.5 volt. Okay, now RMS potential drop across the resistor, across the capacitor at resonant frequency can be given as. So we have calculated RMS potential drop across inductor. Now we have calculated the RMS potential drop across the capacitor at resonant frequency. So VC RMS is equal to IRMS XC, and XC we know that, which is equal to, at resonant frequency, XC equal to 1 upon omega naught C. Okay, so IRMS into 1 upon omega naught C. Putting the value of IRMS, omega naught, and capacitance C. IRMS we have calculated, omega naught we have calculated, and capacitance C we have calculated. Okay, so also we have calculated the XL. So XC will be equal to XL at resonance. So we can put directly the value of XL in this. Okay, but if you are going to calculate it, you can calculate it. Okay, so put the values of IRMS, omega naught, and capacitance C in the above equation. So VC RMS will be equal to, what was RMS given? 8.13 upon root 2 into 1 upon 50 into 80 into 10 to the power minus 6. 50 is omega naught, 80 into 10 to the power minus 6 is C, which is equal to 8.13 upon root 2 into 10 to the power 3 upon 4. Okay, so VC RMS is equal to 1437.5 volt. So VC RMS is same as VL RMS. Okay, hence RMS potential drop across the capacitor at resonant frequency omega naught will be 1437.5 volt. Okay, potential drop across resistor can be given as, so potential drop across resistor is VR RMS is equal to IRMS R. Okay, R we have been given in the question. So VR RMS will be equal to IRMS, we have calculated 8.13 upon root 2 into 40 ohm. So VR RMS will be equal to 230 volt. And also 230 volt is the value of, or voltage of, source. 230 volt is the voltage of the source connected, and also potential drop, RMS value of potential drop across resistor is given as 230 volt. Okay, now since in series LCR circuit phasor VC and VL are out of phase by 180 degree. Okay, so we have seen the phase diagram of LCR circuit. Okay, so VC and VL are out of phase by 180 degree. They are exactly opposite to each other. At resonance, VC and VL is equal, due to which they will cancel the effect of each other. Okay, at except resonance condition, VC and VL are not equal. That's why there is a resultant phasor of VC plus VL. So when we combine VC plus VL, that means VCM minus VCL, VCM minus VLM, peak values of both these voltages. When we combine this and take the difference of these two values without except resonance condition, they are not equal, but they are opposite to each other. So net effect will be taken in one direction and it is not zero. But at resonance, VC and VL are exactly opposite to each other and magnitude of these phasors are equal. So they will cancel the effect of each other completely. So now since in series LCR circuit phasor VC and VL are out of phase by 180 degree, that means potential drop across LC combination, that is calculated as VC minus VL, or we can say VCM minus VLM, or we can write it as VC RMS minus VL RMS. We can write it as in any notation. Okay, so we have calculated also VC RMS and VL RMS, it is equal. So if we are taking the difference, okay, after combination, LC combination, so it will come out to be 0. Okay, so potential drop across the LC combination VCL, which is equal to VC minus VL. So VCL is equal to IRMS XC minus XL. So we know that at resonance XC is equal to XL, which means VCL will be equal to 0. So VCL is equal to VC minus VL. VC is equal to, so this is RMS value. So IRMS XC. VL is equal to IRMS XL. So it will become IRMS XC minus XL. Since at resonant XC is equal to XL, so this VCL, potential drop across LC combination, will be equal to 0. Also, by another method, we can write it as that VC RMS and VL RMS we have calculated. Both have same values. If we are taking the difference, it will come out to be 0. So potential drop across LC combination is 0. Only potential drop occurs across resistor in the case of resonance. Okay. Hence, it is proved that potential drop across LC combination is 0 at resonating frequency. Okay. So this is all about today's lecture of NCERT exercise. I hope you enjoyed the session. Thank you.